Hello everyone. In today's lecture series, let us discuss about the product of sum in Boolean algebra. In the previous section, we have discussed about the sum of products. Any Boolean expression can be represented either in sum of products or either product of sum. In the previous section, we have discussed about sum of products, and today's discussion, we are going to look about the product of sum. So this is product of sum. See the terms in between. The terms are separated by the sum and the sum is separated by product. So product of sums. Product of sums. That is why it is known as product of sum, and in short form it is also known as POS. Either SOP or POS, we have canonical and non-canonical forms of representation. So this is, if it is a non-canonical form of representation, then we know that every term, here it is sum term. If it is SOP, it will be product term. Yes, here in sum term, all the variables should be available. Here in this second and third terms, see here A is missing and here B is missing. So this is non-canonical form of representation. Now coming to this, it is the canonical form of representation. So in canonical form of representation, every term will be having all the functions. So this is a Boolean expression with function A, B and C. So A, B and C. A, B and C. Also the third term also contains A, B and C. So since all the variables are present in all the terms, we call it as canonical form of POS. In SOP, these terms are known as min terms. In POS, these sum terms are known as max terms. This is the POS. In SOP, it is separated by products, right? Here in POS, the same thing, it is represented by sum. So since it is here, there if it is 0, 0, 0, we'll be writing it as x dash, y dash, z dash. Here the inverse it will be x, y, z, which is separated by plus. Okay, this is max term 0, max term 1. Min term we use small m to represent, and for max term we use capital M to represent. Now let us find the canonical product of sum. So this is again an input with a function, the same function as we have seen for SOP. Now write the canonical POS form. For POS, for SOP we'll be using summation. Here we'll be using product because it is the product of all these terms. So here see, we'll be writing this wherever we have the function 0. There we wrote this wherever we have the function 1. So here M0, M4, M6 and M7 are having zeros, and this is the canonical product of sum. And now the function, if you see here, if it is M0, then the max term is x plus y plus z. Yes, so we'll be writing x plus y plus z, and similarly all the 4 terms, which is 11 to M0, M4, M6 and M7. So this is an expression to find the non-canonical form. So after finding this, this is a canonical form because all the max terms contain all the variables. Canonical forms, when it is been realized, the number of gates will be more. So in order to reduce the number of gates, we go for non-canonical form of representation as well as minimal representation. So to find non-canonical form of representation, we'll be using Boolean laws. Then this is minimal product of sum. So this is minimal product of sum. That is, after the non-canonical form, in order to reduce it to further extent, we use K-map to find the minimal product of sum. Here in K-map, for SOP, we'll be grouping ones. Here we'll be grouping zeros, and we'll be finding the minimal expression. You see here, this is the minimal expression, and this is the canonical expression and this is the minimal expression. So if you see how many gates have been reduced, you can realize here you have only 1, 2, 3, 4 and 5 gates. Here we have n number of gates to implement. Right, here we have 5 gates. Here we have 4, 5, 6, 7, 8 gates. Right. So when we go for the minimal form, the number of gates can be drastically reduced. So this is for your assessment. And thank you.